Chapter 8 has to do all with radicals. So 8.1 is actually simplifying radicals, but we're going to talk a little bit about a rational versus irrational number before we get into radicals. So just to start, a rational number is a number that can be written as a fraction. It's as simple as that. That's the most basic definition. So it's a number that can be written as a fraction. So we say p over q with q not equal to 0. Why? Well, because when we have 0 in the denominator, technically the fraction is undefined. So we're talking about any number I can write as p over q. So some examples, 11 is a rational number. 4/3, a rational number. Believe it or not, 0.225, if this whole thing is repeating, it is in fact a rational number. I can write a repeating decimal as a rational number. An irrational number then is something that cannot be written as a fraction. So cannot be written as a fraction. There's no way I could make it as p over q where I could have p and q be integers. That's another key thing here. So p and q have to be integers. An integer is a whole number, a counting number, right? 0, 1, 2, 3, -4, whatever. Examples of irrational numbers, pi, an irrational number, probably the most famous. E, another, it's just like pi, it's an irrational number. Something like radical 2. I can write it as a radical and that's an exact value, but if I put that into my calculator, I'm going to get a decimal that goes on and on and on forever without repeating. I cannot write it as a fraction, therefore it's an irrational number. So you will see some radicals that are irrational numbers. So the set of real numbers, that's what we're writing in here, consists of all rational and irrational numbers. So under real, it branches into rational and irrational. All of these are real numbers. And the symbol that denotes the set of real numbers actually looks like this. It's an R with like an extra bar through it. So you'd write a capital R and draw another staff through the back. So all these times we've been writing all real numbers as our values that will make the denominator true. You really could have just drawn that uppercase R with the slash to the back. It represents all real numbers. So a number is called, we're on to the next chunk here, a number is called a square root of a number if you have something like this. The square root of x is equal to n. That radical sign, the symbol that looks like this, is called a radical sign. And this symbol is used to represent the positive square root of a number. The expression under the square root, or under the radical, I should say, excuse me, is called the radicand. So under the radical, we have something called the radicand. We're going to break apart this radical right here and label it. So if I have a number out front, put a 4 out there, this, just like anything else, a variable with a number out front, this is my coefficient. This number underneath, this 81, is the radicand. And the little sign that tells me what operation I'm doing, this is my radical sign. Sometimes there will be a tiny little number that sits right in here. In this case, if it was a 2, that would tell us we're taking the square root. It tells us what root we're taking. And this little number is called the index. So if that was a 4, I'd be taking the 4th root. If it's not written, we assume it's a 2. So usually you won't see a number written on there and then you can assume it's a square root. Okay, a perfect square, maybe you've heard this term before, is a number such that the square root of x is equal to n times n with n as an integer. Essentially, think about it like this. If you have a square that's perfect, granted I know my drawing is a little off, this side right here was a 3, this side right here was a 3, this would be 9. 9 would be a perfect square. It's something that the sides are nice and neat, they're two of the exact same integers. An example of a non-perfect square would be 10. If you put a 10 here, what number would you have on both sides? It certainly wouldn't be 4 and 4, that would give me a 16. So it must be between 3 and 4. 10 is not a perfect square. So if you think of perfect squares, you could think of, your, like I said, your 4 and 4, 5 and 5, 6 and 6, and the same thing for negative. So negative 1 gives you a 1. 1 is a perfect square. 16, 25, think of all your doubles on your multiplication chart. It goes on, non-perfect squares, -6. Any negative, as far as we're concerned right now, is not a perfect square. So even if you have -9, it is not a perfect square. We're going to get into imaginary numbers later. That's where we'll start to see that. But as far as we're concerned, even though 9 is a perfect square, -9 is not. In order to simplify radicals, we're going to use two different methods. The first method we're going to use is going to be to consider our perfect squares and see if any of them are factors of the radicand. I'm talking about that number under the radical. You might realize that based on the number, you can't think of a perfect square that is a factor. So the second thing we're going to do, which I find to be the most beneficial, is to find the prime factorization. Essentially, that's the factor tree of the radicand. You break down the radicand and continue to factor it until you're only looking at prime numbers. We'll simply look at both of these, and then you can choose what one you like better. If you like prime factorization, you can use that. If you'd like perfect squares, you can use that too. So I'm going to solve them both, and then you can decide which method you like. So if I'm thinking in my head, I think 50, what perfect squares are a factor of that? I think right away 50 is really the same thing as 25 times 2. I'm thinking ahead and planning that 25 is a perfect square. I can split this into the square root of 25 times the square root of 2. This becomes 5 radical 2. So I'm saying the square root of 50 is actually equal to 5 radical 2. That's my perfect square method. Identify 25 as a perfect square that is a factor of 50. Prime factorization says I'm going to break this into a factor tree. 10 times 5, I break this into 5 times 2. And what I'm going to do is circle all of my final branches. I then look, anything that has a buddy gets to leave. I'm going to draw my radical over here. If they partner up, they get to leave the radical. So for example, these two 5s right here, a 5 and a 5, they have partners, they leave the radical. This 2 doesn't have a partner, he goes back under the radical. The number in your index tells you how many partners have to exist in order to leave. If it was to the third power, or I'm sorry, the third root, I would need 3 5s to be partners in order to leave. In this case, since the index is not written, we assume it's a 2, and I only need 2 5s. So the buddies get to leave. I'm sorry, the buddies get to leave, and the singles go back under. Let's do a few more examples and you can see what you're looking at. So I'm going to do 108, the square root of 108. I'm going to start by doing the prime factorization. I know one thing for sure, it's an even number. If I look at this, I might not know a square root off the top of my head, but I do know it's an even number, so I can definitely split it into 2. And something, 2 goes into 10, 5 and into 8, 4, so I'm looking at 54. I can break 54 into 9 and 6, 3 and 2, 3 and 3. I'm going to circle all my final branches. Anything that doesn't have something else coming off of it, all of these numbers should be prime. Anything that has a buddy gets to leave the radical. So these 3s get to leave the radical. I'm going to draw my radical over here. They leave. I notice there's a set of 2s here. Here's a 2, here's a 2. So they get to leave the radical. And this 3 right here doesn't have anyone to partner with. It goes back under the radical. This simplifies into 6 radical 3. I multiply those numbers out front for my coefficient. So square root of 108, I'm saying, is equal to 6 times the square root of 3. It's going to make it a little easier for me to do this one now. If I look at this, I'm saying what perfect square is a factor of 108. I say 108 is really 36 times 3. I know the square root of 36 is 6. So I end up with 6 radical 3. I think 108 is a better example to show where prime factorization may be more beneficial if you can't think off the top of your head what is a perfect square that is a factor of this number. So again, you can use whatever method you want. I won't force you to use one method over another. It's your choice, whatever is more comfortable for you. I'm going to do a few more examples quickly. 54, I can break this into 9 and 6, 3 and 2, 3 and 3. Anything that is left at the end gets circled. Those are my final branches. Buddies get to leave the radical, so I'll put a 3 out front. Anything without a buddy goes back under. So this 2 goes back under, and this 3 goes back under. Doesn't matter which 3s you choose, as long as the two of the 3s go together. So simplifies to 3 radical 6. I'm going to do another example where there's already a coefficient. So I'm going to do 3 times the square root of 8. I look at 8 and think 4 times 2. I know 4 is a perfect square. So this is really 3 times 2 times radical 2. I'm getting this because the square root of 4 is equal to 2. So if I split this 8 into the square root of 4 times the square root of 2, square root of 4 is 2, and radical 8 simplifies into 2 radical 2. I have to remember to take into account the coefficient that was already there. So 3 times 2 gives me 6 radical 2. And that would be my final answer.